everyone. Welcome to my talk about building resilient systems in the face of production chaos. Or, if we're being a little bit more honest, my first decent excuse to put dragons in a tech presentation. Let me introduce myself before we go too deep in. I'm Renette. I'm a technical lead at Intellect. I'm currently working on a project in Standard Bank in the digital platform space. I enjoy reading fantasy books, playing board games or role-playing games, and the fluffy lady you see up top there is my real boss. If I work after 4 p.m. or especially attend meetings after 4 p.m., she gets real angry. For the purpose of this talk, consider me the Dragon Slayer. What's this talk about? When I say resilience, right, it's all about how our code runs in production. We love writing code, putting it into production is extra amazing, but when production falls down, it's not as cool. So I'm hoping to equip you to slay some dragons. 45 minutes isn't very long, so this is going to be a speed run through a bunch of different tools that can help you. What is resilience? Resilience isn't about being faultless. We're never going to get there. Every time you fix one problem, a new problem crops up, and it's harder to fix than the previous one. So, resilience is about our system's ability to recover from faults without humans needing to intervene. And also, if there is a fault, to still provide some level of service in parts of the system. Let me tell you a story before we get into the details. It's late at night, or maybe early in the morning, you're sleeping, when suddenly your phone rings. On the other end of the line is maybe your manager, or maybe the poor operations guy whose job is staring at monitoring dashboards the whole night. The news is dire. There's dragons about. Time is running out. Your manager wants updates every 5 minutes. Customers are starting to get angry, and social media is blowing up because apparently our customers never sleep. I wish they would. And if this goes on much longer, you know the My Broadband guy will earn his paycheck this month by writing about you. I'm sure if you've ever been on production support, you've encountered this exact scenario. So what do you do? In this talk, I'm going to divide it into roughly 3 categories. The first issue is finding the problem. How do we find this problem? The second question is maybe in that crisis incident, we were in fix mode, right? We don't care about what the problem is, we just need to restore service. Afterwards, we need to be able to reduce the problem to both find the root cause and make sure we fixed it. And lastly, it would be great if we could prevent the problem in the first place. In our Finding the Problem toolbox, our first tool would be our application performance monitoring tools. These tools are your Swiss Army knife observability. They do anything. Before I give a definition, some examples could be Datadog, Azure Application Insights, AppDynamics, Dynatrace. They do everything. It's a bit of a black box. It could look something like this, showing all your services and health metrics, or a little bit more detailed like this one. It can do real-time performance monitoring, both for your application as a whole. How does my application's memory utilization look? How does CPU utilization look? And individual endpoints or business transactions. Is the error rate on this specific feature high or higher than normal? It provides alerting when things are detected as anomalies or go above certain baselines. It can alert you. Be careful about alerts, however. If you have too many, it can create alert fatigue, and then everyone just mutes the group and ignores all the alerts. It helps you visualize problems and create custom dashboards for certain metrics to help you quickly identify the problem. And the fancy new modern ones all have some sort of AI-based anomaly detection with mixed levels of success, but the idea is good. APMs are amazing, but they don't always do the trick. So the next three things we're going to talk about is if you go know anything about open telemetry, they were like, there's these three pillars of observability. Now that's by no means exhaustive, but it's a good way to think about observability. But why don't I stop the talk after APM? Why do we need extra monitoring? Sometimes we've got blind spots. You're in this production crisis. You finally figured out what went wrong and you realize, I cannot actually see any of this on my monitoring tools. Third-party systems that are black boxes, maybe a database or a reverse proxy or a load balancer that doesn't integrate nicely with your APM. If you need custom dimensions to aggregate or search metrics by, that's not available in your APM. Or if you want custom metrics. And sometimes redundancy, either to give a different view of the same data, or if your APM tools aren't super stable, which is a whole other conversation. When I say metrics, a matrix literally just something we can measure. It could be defined by your language or framework or something completely custom based on your application and business requirements. Some examples could be the number of successful requests, the average response times for an endpoint, or maybe how many cache hits or cache misses your application has. If we look at a more traditional metric system, what we're going to have is we're going to have some sort of metric store, for example, Prometheus. It might have a built-in database or a separate time series database. It has a mechanism for discovering targets. So it would say, these are all my APIs. Then it would scrape those targets, either applications or third-party tools that expose metrics. And you need some sort of visualization on top. Grafana is a popular one. And there you have your dashboards and visualization. So that's metrics. Just measure something. Pillar number 2 is tracing. The idea is to find the dragons between the applications, to find the dragons in the data flow. We want to visualize the path of requests flowing through a distributed system. If we have a system like this one, on the left side, you can see there's this little graph showing the system. We've got microservice A calling B and E, and B calls C and D. On the right side is an example of how your traces might look like. It creates this hierarchical view that shows you how much time is spent in each application and who is calling what. Sometimes in this view, you might notice weird gaps or just traces that are longer than they should be. Some tools for distributed tracing, I've already mentioned OpenTelemetry. They're becoming the de facto standard for observability. Zipkin and Jaeger are two observability tools from Twitter and Uber, respectively. Cloud native tools, AWS X-Ray, Google Cloud Trace, and some of the APM tools also have tracing functionality. The fourth one is boring, and we have them, but we tend to not use them super effectively. Logs. We all know what the log is, right? It's a bunch of random text that you can't read. It's text with a timestamp. It identifies a specific event. Maybe if you're lucky, it's got some metadata. It could be structured or unstructured. To use them effectively, a few tips. Use your log levels appropriately. Something that logs everything at error level, where it should maybe be debug level, is almost as bad as an obscure piece of code that has no debug logs and then it breaks. You need to be able to correlate logs. If you have a bunch of log lines, you need to be able to say, hey, these belong to the same request. You need to maybe be able to correlate log lines between different applications as this request flows through your system and maybe associated with certain traces. They need to be searchable. Ideally, make them structured and add enough metadata, but also ingest them into some sort of system, maybe your Splunk or your Elasticsearch or your APM. The last thing you want to do in a crisis is go look at 20 different containers to try and figure out and find a specific event that went wrong. Include important context. Something went wrong. Cool, okay, bye. That's helpful, right? Include important context. If something went wrong, what went wrong? If input is invalid, what was the input and why is it invalid? And an interesting one is consider having the ability to change log levels without application restarts. A lot of the time, when something's weird, if you restart your application, it's going to go away. And that's cool for now, but it's going to happen again next week or next time. It is important when you're dealing with resilience engineering to make sure the same problem doesn't happen again, because then we've made no progress. In the observability world, the current favorite buzzword seems to be wide events, right? It's really, really simple. The idea is just take everything we've gotten so far and smush it together. For each request, have a single context-rich event or log or trace per service hop. The reason why we want to do is it's because it's context-rich. We can query it across many, many dimensions. It helps us correlate events because they're now all together in a single document. And it's helpful for multiple use cases. If you have outages, if you need some sort of business analytics, or if you need to investigate individual customer incidents. I haven't found good open source cross-platform tools for this. A lot of people argue, oh, this is just the same as structured logs. Sure, just like add all the metadata and all the context. Some people argue, oh, this is just traces. Once again, it could be just add all the context, or you can build a custom solution that works for your framework of choice and your business needs. We've gone through general observability tools. Now I want to talk about two very, very situational ones that have been lifesavers for me in dealing with production incidents. The first one is thread dumps. The idea is what we want to take is a snapshot of the state of all the threads of a process at a specific point in time. This is especially important if you deal with older web applications where every incoming request is associated with a thread. Why would we want to do this? If our application is unresponsive, if some of our thread pools are exhausted, if our APM is reporting stuck threads or deadlocks, if there's some sort of inexplicable bottleneck or thread contention or high CPU usage. This isn't really a thing you can monitor continuously, so you would probably do it during an incident if you're trying to reproduce or debug, or if you suspect weird behavior, you could do it repeatedly over time to compare it. This is a snapshot. It won't show you behavior over time like all the previous tools, so it's very situational. How you would do it, a lot of the APM tools can do it for you, especially if they attach to your process using some sort of agent. You could do it programmatically and expose it over an endpoint, but this might be problematic if your application is already non-responsive. Some languages have specific tools or CLIs that can help you do it, and operating system can do it. Certain kill commands on Linux, for example, can trigger thread dumps in Java. Your thread dump would look something like this. It's plain text. You could try to read it if you want to, but it tends to be not super helpful. It shows you the name of every thread, the stack trace, if it has any locks associated with it, and maybe the state of the thread. Luckily for us, it usually doesn't contain sensitive info. So if you want to analyze it, you could go look for online tools. But also, many times your IDE will have the basic thread dump analysis capabilities. It could show you things like the states of your threads. Are they blocked? Are they runnable? Are they waiting for something? They could maybe identify threads with the same stack threads that are all waiting for the same resources, and sometimes show potential problems, but you'll have to know your application to know if these problems are legit, unfortunately. The next snapshot tool we have is memory dumps or heap dumps. And before I go further into this, important myth that needs to be dispelled. Yes, even if you have garbage collection, you can still have memory leaks. I've caused my share of them, I've debugged my share of them. I have a whole other talk about garbage collection and how this is possible. But just know it can happen. So what the heap dump is it's a snapshot of all the objects in the process memory at a certain point in time. Once again, a snapshot, so things are sounding very similar. Why would we do it? Aforementioned memory leaks. If you just have high memory usage and you want to know why, if you're getting out of memory errors, or if you're observing weird garbage collection patterns. When would you do it? Same rule as last time. During the incident, while you're trying to reproduce it, or maybe frequently if you're trying to compare. How would you do it? This is once again the same as earlier, your APM tools maybe. There's operating system tools that can do it, or language-specific tools. Heap dumps are a lot harder to analyze than thread dumps. First of all, they can potentially contain sensitive information, so don't just go for a random online analyzer. And secondly, it likely depends on language-specific memory layout details. This screenshot is from a Java memory analysis tool called the Eclipse Memory Analyzer. It can show you things like, this is how my class histogram or my object histogram looks, or these are the likely leak suspects if you have a memory leak. Now, finding the problem is all good, but in that moment, our main focus is get production back up. Afterwards, we can worry about what was the root cause and let's prevent this. To do that, we need to reproduce the problem. The first one's obvious. We need load tests. If these things happened under low load, we would have caught it in the test environment. We wouldn't have waited for production. The idea is throw a bunch of load at your application, but do it under non-ideal circumstances. Get it as close to production as possible. If your production workload has different resource allocations, different memory or CPU allocations than your testing workload, your load test is not going to be as effective. When you're doing a load test, figure out what your goals are before you start. Are you trying to push it to see how far it can go before it becomes unresponsive? Are you trying to see if it can handle sustained load at a certain threshold? Are you trying to see what happens when it gets weird load spikes, sudden load spikes? Look closely at your results. Oftentimes we do load tests and go like, our application is clearly fine, the response times are amazing. Not noticing that the reason why the response times are amazing is because the error rate has shot through the roof. Simple example. And lastly, be proactive. If you're doing a major upgrade or building a major new feature or introducing significant new components in your architecture, do those load tests before prod falls over, please. This is a lot easier said than done. If it was easy, we would all be doing it and not having this talk. Mimicking production is hard because we're not just talking about our system, we're also talking about all the components around us. Scaling to the scale of production is often expensive and maybe near impossible, so you might have to adjust your load tests and try to do some math to figure out how does this relate to production. Data. Oftentimes in production, our data is a lot larger than in our test environments. And to properly mimic production load, we need a variety of different users with different types of profiles. The network in the test environment always seems to behave. The network in the production environment almost never behaves. If there's any network engineers in the room, I am sorry, you can come shoot me afterwards. And well, it's great. We can like, cool, we've load tested our application. A lot of the times we can't actually do it because our downstream applications may be owned by different tools, even different teams, different business units, might not have the scaling capability we need in the testing environment to do proper load testing. Some helpful tools for load testing include Apache JMeter. This is old and ugly, but it works well. The only problem we have with it is it's not great for version control or sharing data. It's all like proprietary XML formats. But if you just want something quick and dirty and you know how this works, it's really effective. Tool number 2 is Gatling. It's an open source load testing framework, and you get to write your load tests in code, Scala specifically. It's got both open source and enterprise version available. And the nice thing is, since it's code, we can both reuse components and version control it fairly easily. The third tool I want to highlight is Grafana K8. So that is a load testing framework from the Grafana people. You write your load tests in JavaScript. And the really cool thing is they provide a bunch of metrics, and then you have like a Grafana dashboard out of the box for it. These metrics are for your load tests. You still have to monitor your application metrics using your APM or whatever, but it can give you some really helpful information. Up next is to get back to that non-ideal circumstances thing, right? Unfortunately, a lot of the time, production only breaks when it's the perfect storm. I've done my load tests, my application can handle all this load, and then suddenly we come to production and that other system is down and that other system has slowed down, and there's like weird packet loss things being reported here, and suddenly my application falls over. So we need some tame dragons. This is not to talk about chaos engineering, and I don't have that much time. So I want to highlight just one tool, and this tool is called ToxiProxy. It comes from Shopify's chaos engineering suite, and the idea is to simulate weird network conditions. It's really, really flexible. There's two components. There's the proxy, which you then put in front of whatever network calls you make, and the CLI that allows you to modify the proxy on the fly. So you can change the circumstances as your load test is happening. And it's a very flexible deployment model. You can get the binaries and run them directly, or you can use the Docker images. It can do a bunch of things. Simplest one, add latency, make things slower. It can limit bandwidth. It can delay socket close, maybe if you got like weird behavior where connections are held open too long sometimes. It can also do the opposite, close connections early, maybe before all the data has been received. It can slice up TCP packets into more and simulate TCP resets. All of these things you kind of help you simulate when things go weird outside your application. Now, finding the problem and reproducing the problem is all good, but we've all been taught that prevention is better than cure. So let's talk about how we can prevent a lot of problems in the first place. If you take one thing from this talk, is put timeouts on everything. When you make HTTP calls, when you try to get database connections, when you're connecting to your message brokers, when any kind of IO basically, have timeouts. Don't tell me, oh, we're relying on the default, unless you can very, very confidently tell me what that default is and that it will not change. A lot of the time, default means, oh, we're going to be using the operating system default. And then the operating system default is, there is no timeout, or it's something ridiculous like 5 hours, which doesn't help us. Our customers tend to get cranky if the response time on the website or mobile app is more than like half a second. So 5 hours isn't acceptable. The second one that's helped us a lot is enabling connection reuse. Connection objects, TCP connections, HTTPS connections are very, very expensive to create and tend to be somewhat fragile. So not having that extra time to create a new connection helps improve response times. Even more, it compounds. If you have like 5 different hops and each one makes a new connection, if you just remove that extra little bit, it compounds. It improves resource utilization, because instead of making a new object and then garbage collecting it and making a new object and garbage collecting it, and also making a new socket on the operating system and then closing and releasing it, we reuse them, so improved resource utilization. It reduces the snowball effect. Suddenly, when something goes funky with DNS or My database is slow to open new connections because it's under strain. It doesn't affect me with every single request anymore, only when I'm refreshing my connection pool. And yeah, overall, if you start applying this across your entire system, it will improve your resilience and performance. Where would you do it? Well, the answer is once again everywhere you can. But if we make it a little bit more specific, databases. That's like if you start doing connection pooling and connection reuse, databases are the most often use of this, but not the only one. HTTP connections. If you use HTTP 1.1 or HTTP 2, or if you're like really on the cutting edge and using HTTP 3, all of those let you reuse connection objects. HTTP 1.0 does not. And often our basic HTTP client will default to 1.0 with no connection reuse. If you have message brokers, once again, try to make connection pools instead of opening new connections every time. Don't just do this on your applications. Also look at your load balancers and reverse proxies, especially if we're dealing with layer 7 load balancing where it has to make a new TLS connection to the backend. And any other network components that you know of in your stack. So that is connection reuse. Pattern number 3 is circuit breakers. Circuit breakers sit in your code, and the idea is that we want to both fail fast when things are wrong. If we know something is breaking, then we might as well fail quickly instead of waiting 5 seconds or 10 seconds to fail. We want to prevent resource exhaustion. Often what will happen is all your application threads are busy waiting for that other downstream application, and we can serve no more requests. We want to recover gracefully and also reduce pressure on the downstream system. So how will it work? The idea is this. We have a client, the client has a circuit breaker, and it calls some sort of supplier. When we observe repeated failures, maybe timeouts on that supplier, at some point the circuit breaker is going to trip, and then instead of even trying that request, it's just going to fail immediately. After a while, depending on your configuration, it's going to start trying a low percentage of requests again, and if they pause, the circuit breaker will close and we're back to normal. Otherwise, circuit breaker will stay open. Pattern number 4 is bulkheads. This one is less well known from what I've seen, and this becomes very, very important if you have one application that does many different things. The idea is to isolate parts of your application. The term originally comes from container ships, where the bulkhead would be a door or something that if one section of the ship is breached and it starts flooding, it prevents the rest of the ship from going down. Once contained, the ship can continue doing its thing and we're not dead in the water. If we go back to the dragons, maybe the idea is install some fire doors in your castle. If one tower burns down, we can hopefully isolate it and prevent the rest of the castle from also burning down. How we're going to do it in practice is by preventing or limiting concurrent calls to a specific method or supplier or downstream system. And this is going to help us limit the scope of downstream failures. So say we've got this microservice A, it has 2 features, the one does X, the other one does Y. If we share a connection pool or a thread pool between the 2 of them, and something goes wrong on the connection between A and X, it could potentially affect feature Y. If we instead isolate them and something goes wrong on X, we can still reliably serve feature Y, which goes back to the definition of resilience. Even when things are happening and things are going wrong, we want to enable some customer functionality. Number 5 is fallbacks. And the idea is there's a bunch of noise in our system, there's a lot of errors, but non-critical errors we can maybe ignore or provide some sort of fallback behavior. what it boils down to in code is we're going to say, if an exception gets thrown here, if an error occurs here, do this other thing. That could be return a default value, return a cached value, get the data from some other source. It allows our customers to continue with limited functionality. For example, in Standard Bank on the banking app, if the system that fetches balances for your account is unavailable, we display you a cash balance as long as we have a balance from like the last 24 hours or something. You can still continue with limited functionality. Be careful about fallbacks, however. If you do it too deep in, too close to a source system, other systems that rely on you might accept it as truth. We've had incidents where, oh, this system says this feature isn't available. And another system was like, oh, this feature isn't available. I'm going to update your profile to say you don't have this thing anymore. And then it says that. And then customer data gets messed up. So be careful about where you use fallbacks. Apply it carefully. But it is a very useful tool. That is my speedrun through resilience engineering. The conclusion is there's no silver bullets. To build a resilient system, you have to know your system. And when things go wrong, you have to understand why it goes wrong. And more importantly, build a culture of constant improvement. When something goes wrong, do your blameless postmortem, find a root cause, fix it, and make sure it doesn't happen again. And if you know of this theoretical problem that will only occur during the perfect storm, it might take a while, but I promise you that perfect storm will come. That is me. Thank you. Any questions? We've got a hand there at the back.
Thank you for the talk. It was quite insightful. I'm just curious, so what would you say is the best or recommended approach for a junior on a team or on a project that is quite a legacy project that is riddled with potential prod issues?
Honestly, well, first of all, I would hope you have seniors in your team you can take guidance from, right? And your best buy-in to get time to fix these things is going to be figuring out which ones actually cause the most customer friction. A lot of the time, there's not much buy-in because we could be building features instead, right? So you'll have to sell it, and the best way to do that is most likely figure out which ones cause the most customer friction, which ones are easy win. And also just maybe the scout rule, right? If you touch a piece of code, just leave it better than you found it before. That applies both to code quality and resilience patterns. You're unlikely to get buy-in to fix the whole thing at once, refactoring it, add circuits breaker everywhere, but maybe you can apply some timeouts easily, and that would already help. Or maybe just improve monitoring so you can actually figure out what's happening. But yeah, low-hanging fruit that's easy to fix and customer friction.
Nothing else? Thank you.
Thanks, everyone.
Oh, wait.
Ah,
Yes, one.
I can't see the hands really.
I also can't.
Hi. Recently, Microsoft has an issue where the update is said to crash SSDs, and they say they are failing to reproduce that because for some odd reason they say no, it's not their fault. In a case like that, how would a company like be able to reproduce errors they can't find, but the customers say they are there?
That is very, very hard, right? So, and what it's going to boil down to is you're going to need, unfortunately, some sort of monitoring or logs or something on your customers' devices. So there's a ton of tooling out there that helps with this idea of real user monitoring or analytics, stuff like that, that sits on the customer device and sends you usage data. And then sometimes the best you can do is recreate this problem as close as possible. Get that same device, set up a customer profile that has the same products, the same features, similar kind of setup, right? And sometimes we just can't fix it. And I don't have the answer to that.
Some of the bars that they just reboot, then still the SSD's gone from the system with it up. So you actually, some of the bars actually shut down, and that actually brings it back up in the bars.
Okay, so what he's saying is tell your customers to restore their BIOS. I'm sure they'll appreciate that.
Stuff as well. That's cool. I'm good.
So I've got a question. In gathering telemetry data, we gather a massive amount of it, right? In general, so because we do not know when the problem will arise. But in general, how do we reduce the noise so we can actually get to the data we needed to see in the first place to see what is wrong? So because I find with tracing, we see an error, but it's already 20, 30 traces ago. And now we have to find the logs and the metrics and everything else that is related to it.
So correlation, right? You need to be able to, if you're saying now you have to find a matrix and the traces related to that. So you need the easy way of doing that. Automated anomaly detection, like computers are really good with patterns and things that don't follow patterns. And that's one of the driving factors between the YDO and two, right? Is this idea of instead of 50 traces just inside this one application, let's consolidate it into one event to at least bring the important context together. And it definitely helps if most of your telemetry is in the same system. You don't have to go like, oh, I've got an APM, and I've got a Grafana, and I've got an Elasticsearch, and I've got this other thing, and you have to like try to correlate it across all the different systems. That really makes it harder. So if you can bring things together, that helps. No more questions? There's more at the back.
It's a totally unrelated to tech question. Given that I'm probably the least technical people person in BBD, where did you buy your skirt? It's gorgeous.
Thank you. Yeah, I'll see you afterwards. Hey, I spoke fast.
I picked up interest in something you've mentioned around the wide events and correlating everything into a single event with sufficient context. When you talk about this wide event, is this a single event at a particular with a single timestamp, or is this an aggregated view of the events that you've correlated? So I'm trying to understand, are you combining the events into one, or are you taking all that context and potentially putting it in a single event with a single timestamp, which you still correlate to the original events?
So look, the idea with wide events is you do whatever you need to do. There's no wrong or correct way, right? The way I've done it is what we do is every time you make a request into a specific application, most of our world in digital space it's all synchronous, so it's all HTTP. You make an event when that call comes in, you go like, this is the start time, this is the end time, and then these are the downstream calls it's making. And then when it makes a downstream call, once again, you've got an event and you can then correlate them to put all the pieces together. the recommendation is generally like every time you make a service hop or a network request go out of your application, make that an event. But it's not a strict standard. You can do what works for you and what solves your problem. Thanks for coming, everyone.